Hello students, welcome to my class of Electrostatics in Dielectric material. In the last two classes, we have seen the electrostatic potential and electric field expression for electric dipole. Now today we will start the electrostatics of dielectric material. Now, what is dielectric material? Dielectric material is a insulating material, and you know there are three types of material we can have. One is conducting material, another is semiconducting material, and third is insulating material. So, dielectric material is one type of insulating material. Now, in this type of material, what happens? The outermost electrons are very much tightly bound to the nucleus, so they cannot move freely in the material. But in conducting material, the outermost electron are loosely bound, so that's why they can freely move. So this is the difference between insulating material and conducting material. So that's why the in the dielectric material or insulating material, the freely available charge are very less. Now, why the name is dielectric material? So, it is due to the application of the material. So, the dielectric material is used to store charge in capacitor. So, that's why this is called dielectric material. Now, there are two types of dielectric material. The molecules of a dielectric can be classified as polar and nonpolar molecules. In a molecule, the protons or positively charges may be imagined to be concentrated in effect at a specific point within the molecule. So here the positive charge is concentrated at the center of the atom. So this is called the center of gravity of positive charge. Now likewise, there is a center of gravity of negative charges also. Or here the negative charges are these distributed electrons. Here the picture is very much simplified. We have considered this is spherically distributed electrons, or s orbitals electrons are spherically distributed electrons. So the center of gravity of this negatively charged electron at the center of this atom. So here the center of gravity of positively charged and center of gravity of negatively charged coincides. So these molecules does not possess any intrinsic dipole moment. So for example, symmetric molecules like H2, N2, O2, CCl4 and monoatomic molecules like helium, neon, argon, etc. are all of non-polar molecules. Okay. Now let's see what is polar molecule. Now inside the dielectric material, if the two charge centers of molecule do not coincide but are separated from each other by a small distance, then the molecule possesses an intrinsic dipole moment. So it is called polar molecules. So here there is no intrinsic dipole moment because the charge centers are not separated due to the symmetric structure of the atom. But here, due to some chemical property of the molecule, the charge center are separated. So here we get a intrinsic dipole moment. So and it is called the polar molecule. For example, asymmetric molecules like H2O, H2S, and ionic molecules like HCl all are of polar molecules. Example of polar molecules. Now let's concentrate first on non-polar molecules and what is dielectric polarization. So first we will discuss about non-polar molecules. Now in non-polar molecule already we have seen that positive charge and negative charge at the same position, that is at the center of the atom. So in absence of external electric field. Now if we apply electric field, this positive charge will experience a force along this direction, and negative charge will feel force in the opposite direction. So they will be separated. So when they will be separated, and as the charge, positive charge value and negative charge value is same, we can consider this is a dipole that we have seen in the last class. And what will be the dipole moment here? And this we will call as induced dipole, right? So the induced dipole moment, the value will be QD, and here Q is what? If the atomic number is Z, then Ze is the charge of the electron, right? Then here this D is actually the equilibrium separation. Now what is this? So at equilibrium, the external field push the nucleus to this right side, and negatively charged will be pushed along this side. So the so at equilibrium, what will happen? This force due to the external field will be equal to the force between these charges, positive charge and negative charge, and that is the attractive electrostatic force, attractive electrostatic Coulomb force. So that Coulomb force and this external force due to this external field will be same at equilibrium, and they will be separated in at this equilibrium, this separation. So at equilibrium, the electric field, external electric field, and the electric field produced by the electron cloud will be same. Now we have to find out this electric field due to electron cloud at the distance d from the center of the uniformly charged sphere. Now to find out this, we have to apply the electrostatic Gauss's law. Now the total charge enclosed by this Gaussian surface having the radius small d will be q prime equal to 4 by 3 pi dq into rho. So here we are considering the charge are uniformly distributed over the sphere. So this rho is uniform. So how to find out this rho? So we know the total charge is small q. Then if we divide by the total volume of the atom, then we will get rho. And here A is the radius of the atom. So volume of the atom is 4 by 3 pi a cube. So q prime becomes q d cube by a cube. Now if we apply the electrostatic Gauss's law, then the electric field due to the electron cloud into the area of this Gaussian surface, that will be the total enclosed charge by this Gaussian surface by epsilon naught. Now here the surface area of the Gaussian surface is 4 pi d square. Then we can get the electric field due to this electron cloud is q prime by 4 pi epsilon naught d square. And if we put the value of q prime here, then it becomes qd by 4 pi epsilon naught a cube. So at equilibrium, the value of the external electric field is same as the electric field due to the electron cloud at d point. Then we can tell that the external electric field value is also this. So from there, the equilibrium separated distance d can be written like this, right? So why we are interested to find out this equilibrium separation? Because from here we can find out the dipole moment. So let's find that. So this is the induced dipole moment because we are applying the electric field and we are getting the dipole moment. So the value of the dipole moment will be p equal to qd, and so if you have put the value of d here, then it becomes 4 pi epsilon naught a q 1 by q. Then q will cancel and the value we get like this. Now if we do this adjustment, then it becomes 3 epsilon 0 capital V E. So here capital V is the volume of the atom, and we can get that this is a constant, and this constant is proportional to the volume of the atom, right? So the here the dipole moment P is basically the proportional to the electric field, right? And this proportionality constant is called the polarizability. So polarizability we can define it like this: the dipole moment per unit electric field is called the polarizability, and here this polarizability is called the atomic or electronic polarizability. And for a non-polar molecule, the atomic or electronic polarizability is proportional to the volume of the atom. So this is very much simplified picture, and this is a very crude model, but the expression whatever we are getting is not too bad if we compare with the experimental result. Okay, so in the next class, we will discuss about the polar molecules and how they are, if we apply electric field, how they will be oriented, what will be the orientation of the polarization, and what will be the force will be applied on a electric dipole if we put it in a electric field. Okay.